the concept of this video is about law of exponents. And so there's lots that go into this. You have to know a bit about exponents before you can kind of get into the properties or laws. So first of all, what is an exponent is something should be addressed. So an exponent is the small number attached to a base, right? So let's say you've got 3 to the 5th, right? This 5 is the exponent, and the meaning of that 5 is repeated multiplication, which means that the 3, the base, so this is called the base is being multiplied the exponent's amount of time. So 3 times 3 times 3 times 3 times 3 times 3. So the base shows up 5 times. That's kind of how that works. And just as a side note, this is called expanded form, right? Writing out an exponent in terms of its multiplication. So the exponent is it's a shortened form of repeated multiplication. A coefficient is different. It's very similar though. A coefficient is repeated addition. So if you have repeated addition, that doesn't change an exponent, it changes a coefficient. So let's say you have x being added to itself 4 times. This doesn't become x to the 4th, it becomes 4x. So your coefficient changes when you add, your exponent changes when you multiply, okay? So they should never both change at the same time if there's only one operation showing. So just something to keep in mind. Okay, then we have special types of exponents. So now that we get just like your basic 1, 2, 3, 4, 5, what about 0, right? What about 0 as an exponent? Well, 0, remember, is always the digit 1. And it's because if you think about like 2 to the 3rd is 8 because there are 3 2's, right? And then you've got 2 squared, which is 4 because there are 2 2's. So essentially we're dividing or taking away a 2. And so as we take away a 2, we're dividing by 2, dividing by 2, dividing by 2. When you do that, you'll always end with a constant of 1 as a 0 power. So keep that in mind, that no matter what the base is, whatever is getting that 0 power, the value is always 1. Negative exponents, if you kind of keep going, so we just had 2 to the 0 is 1. If you go into the negatives and we continue that same pattern, you get 1/2. 2 to the negative 2, when you divide 1/2 by 2, you get 1/4. Essentially, they become the reciprocals of the positive power, okay? So essentially, you take, let's say you've got, 4 to the negative 3rd. Essentially, that negative becomes the fraction bar, and it's just 1/4 to the 3rd. So it just puts it in the denominator, essentially. So let's talk about the properties. There are 3. Or laws, whatever you want to call them. The first thing would be if you are multiplying 2 bases and the bases are the same and they both have an exponent, you can combine by adding. So an example would be something short just to kind of get you to understand. X squared times x to the 3rd is x to the 5th. And the reason that's true is if you expand this, x times x, and then times 3 of them, you have 5 x's. It's all about counting. Okay, so the trick here, or the rule, is to add exponents. Division works a little similar here. Essentially, if you've got a base with a power and the same base with a different power, you can simplify by subtracting. So let's say you've got x to the 4th over x squared here. Essentially, this becomes, the argument is to subtract and get x squared because you do top minus bottom. Why does that work? Well, if you think about the top having 4 x's and the bottom having 2, right? We can find the partners that pair up because x divided by x is 1. Here's another x divided by x, which is 1, leaving me with 2 x's, or x squared. So that's why that subtraction trick works. The last one is a power to a power. So you already have an exponent and we're raising it to another power. The trick is to multiply. If, again, you want to see what that actually means, let's say you have x squared to the 3rd power. Well, I could rewrite this as x times x to the 3rd power. This 3 means there are 3 sets of parentheses. Okay, so if I were to rewrite this, it would be x, and then there's another one, and another, right? So there are 1, 2, 3, 4, 5, 6, x to the 6th, and that's where that trick is, that you could just multiply them. But again, if you don't remember the rules, it's not a big deal. Just expand it, and you'll be able to kind of see and count and figure kind of by process of working through it, you'll be able to see what you need to see. So let's try some examples. So something like this might present itself, and all it's leading to is you getting rid of the negative. So we're looking for 1 over z to the 7th. That would be enough to simplify that. Or something to the 0 power, understanding that that is going to just be 1 and simplifying there. 8 to the, or x to the 8th and x to the 10th, if you don't remember, you could list out 8 of these, 3, 4, 5, 6, 7, 8, and then list 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you can list these all out and then count, or if you remember the rule, this becomes x to the 18th. Notice that there are coefficients of 1 here, and while I did add the exponents, I do not add the coefficients. Those two things do not go together. You would still multiply the numbers, you would add the exponents, okay? The thing I forgot to mention is that exponents always kind of run one set behind of what's happening. So if you see multiplication, an exponent's going to lag behind one step. If you see division, an exponent's going to lag behind one step. And if you see an exponent, it's going to lag behind one step. So just kind of keep that in mind. So here, looking at x to the 14th over x to the 3rd, again, we could list it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, over 3 of them, right? So, I mean, I could wipe out these 3 and these 3 and then count them up. Or I could subtract and get x to the 11th. Here I have 6 f's, 1, 2, 3, 4, 5, and then I have 3 of those, right? So I can do this again and again, and then count them, or just multiply here and get f to the 18th. This is a tricky one because a lot of times people want to multiply the bases, but the base is actually not changing. We're not ever changing. So we have 2 4's here, we have 5 4's here. We have a total of 7 4's. That's all I'm really worrying about here, okay? Same thing here. I have 5 8's over 1 8. This partners up and cancels, leaving me with 4 8's, or subtraction because there's a secretive one there. Last case here, you've got 3 2's, and then this means there's 4 sets. So I would do that 4 times. And if you count all of those, you have 12 2's. A few more examples, just a little bit higher up. If you think about this one, if you have a 3, and then remember you have 4 m's, and then you have a 12, and you have 9 m's, 2, 3, 4, 5, 6, 7, 8, 9. You are going to multiply those still. That's still the case, so that becomes 36, and then you'd have to count m to the 13th. This one's a little different. Remember, you're still going to use the operation for your numbers. So you're still going to do, 6 divided by 2, which is 3. And then your x's, you have 3 x's on the top and 1 x on the bottom, giving you x squared. Last one, I've got 5 with 3 x's, and I have 2 sets of those. So multiply these, get 25, x to the 6th. So these are just some extra examples. If again, I notice how I'm really not using the rules too much. I'm expanding and counting and multiplying. If this went too fast, or if you're still confused, please reach out or come see me, and we can kind of break it down more.